Welcome to this live webinar on overview of MPD well designed by Mr. Nitin Kulkarni, drilling engineer with specialization in MPD and UVT techniques. Thank you for joining in this workshop. Now, without wasting any further time, I would like Sir Nitin Kulkarni to start this introductory session. Thank you. Over to you, sir.
Yeah, thank you, Niharika. Thank you, Nikhil. Am I audible? Are you able to hear me?
Yeah, it's perfect, sir.
Okay, good. So thank you very much for organizing this webinar, and have a greetings to all the participants. Thank you for joining this session. Just to give you a quick background of me, basically, I used to work as an MPD engineer before with Weatherford, and then briefly with Schlumberger. And then later on, I joined oil companies where we were actually deciding on whether we can use MPD on certain wells. So initially, we were from the I was in the service side, then actually in the oil side where we could utilize this technology. So that way, I had an opportunity to see both sides of be on both sides of the table. Where one is when you propose to use this technology to drill a particular section of the well, and then you also are on the other side where you get the feedback and you discuss with the management, you make a proposal to basically get the approval to see if the management is interested and is going to approve this. The geoscience team, the completions team, everybody in the oil company needs to agree before we can go ahead. This involves a certain modification to the conventional method. Now, today's webinar is an overview of well design. So we focus on the well design aspect, assuming that we are going to drill a well, a particular section of the well using MPD. We will basically, we will review certain aspects of what changes we need to do in the particular well design. So certain changes are to be incorporated. And as this is usually important when you are in the beginning phase, but as you move along and as you develop this technology for your field, for your drilling operations, then these things become part of the routine procedure. But this is particularly important when you are doing it for the first time, when you are doing it in the very initial phase. And as I said, if you are doing multiple wells, then on the second well, third well, fourth well, these all become routine procedures and everybody becomes familiar. Okay, so let's quickly look at the fundamentals of hydraulics. Here you have the difference. You'll see some equations on the screen. In conventional drilling, you would see that you have your hydrostatic pressure and your annular friction pressure profile. We discussed about this a little while ago. But what happens in managed pressure drilling is you have an additional component of surface back pressure. And if you break down the equation, you will see here at the bottom, you have the calculation for your hydrostatic pressure, your calculations for friction pressure, and you have your calculations of surface back pressure. And this is the equation that we are all familiar with. Most of us would be familiar with for calculating hydrostatic pressure. If you see, you take into account true vertical depth. So in this example, if you calculate hydrostatic pressure, the equation would be if you have a 10 ppg mud system and your total vertical depth is 10,000 feet in a 1/4 inch hole, your pressure at the bottom would be 5,200 psi. A point to be noted here is that the hole size and the measured depth are not of any importance over here. The mud weight and the total vertical depth is what is, and the constant, which is 0.05, is what is required. So what is friction pressure loss and why are we so concerned about it? Friction pressure loss is pressure loss that occur due to resistance of the fluid in the flow, for example, inside a pipe, through the annular space between wellbore and drill string, and basically all the way through. Friction between the fluid and the pipe creates pressure against the pump. So the mud pumps that we use on the rig, the pressure that is created against those pump, and this pressure the pump has to overcome in the circulating system in order to ensure that the fluid moves from the pump all the way to the bottom of the well, to the surface, and then to shell shakers. So what are the different factors that affect friction pressure? Now, the factors, these are important things because when you start designing a well, whether conventionally or with MPD, you need to know these variables because it is possible that you can change these variables to change the pressure in the well. Now there is flow rate, there is rheological properties, there is flow regime. Flow regime is your turbulent flow or laminar flow, your effective flow area, and the length of the flow path. So these are some of the factors that affect your friction pressure loss. Now there are some mathematical models available to calculate friction pressure loss for different rheology and flow regimes, and we will quickly have a look at them here. Now, what happens is when you when you circulate flow, your flow regime could be either laminar flow and or turbulent flow. Now, the flow regime is decided by something what we call as Reynolds number. So, Reynolds number is if it is more than 2100, your flow would be laminar, it's turbulent. If it is less than 2100, it would be laminar. You know? And in general, we usually have in the drill string turbulent flow, and in your annulus you have laminar flow. So it really depends upon how much annular space you have. Although this is not always valid, this assumption is accepted for calculations. And these are the equations that we have here without going too much into the details, as this session is will not probably have enough time to go through it in details, but in our future sessions when we do the actual training courses, we will discuss all the equations in details because they are used for calculations, and inside even the software, these are the equations that are used. So here you see how you calculate laminar flow. It's less than 2100. So the flow regime is laminar. Then a particular set of equations are used to calculate your friction pressure loss. If you have a turbulent flow, then you have another equation. So in this case, since the flow regime is laminar, we have used this equation to calculate the pressure loss. And after you multiply, for if you have a pipe length of 1000 feet, if you multiply it for by 1000 feet into the PSI per foot that you have established here, calculated here, your total friction pressure loss in this particular case is 807 PSI. So this is how you establish your friction pressure loss. This friction pressure loss in the annulus is what we are concerned about, and this is what has an impact on your bottomhole pressure. So in general, your friction pressure loss would be a function of your length of the pipe, diameter, flow rate, flow properties, that is density, viscosity, yield point, and other rheological values. So in practical world, you usually have a number of softwares to calculate these, and they will give you values, and you normally see that the observed values are different from the predicted or calculated values. Why? Because your pressures, your dimensions of the hole typically are not ideal when you calculate something in simulation or mathematically. You consider your hole to be perfectly the same ID, but in real world, your hole might have some washout or might undergauge, or there may be some dog legs, and this has an impact. So you will always see your calculated and your actual measured value difference, but this is something that I just want to discuss here so that you don't get unnecessarily too much worried about it. Now, what is surface back pressure? This is the term that is quite commonly associated with MPD. So to begin with, let's say even if your choke is 100% open, MPD system will generate surface back pressure. Surface back pressure is generated using your choke, but there are other factors that can add to the surface back pressure, and that is your flow line, your choke manifold, the valves that are part of the choke manifold, the mass flow meter, that is the Coriolis mass flow meter. All of them add to surface back pressure, and this is called as system surface back pressure. So we should be aware about it, that even if you don't intend to apply any surface back pressure, your well will have surface back pressure, and this needs to be modeled right in the beginning of planning. So you may have 50-60 PSI of surface back pressure anyway, just because of the MPD system, and you need to factor that in your calculations. So this is part of your MPD design process. Now, the surface back pressure will change when you change your flow regime. So you need to model it for different flow rates, and you need to measure it for different flow rate. And one more thing we need to keep in mind is that whenever you're going to apply surface back pressure, the MPD choke would require flow through it during drilling or connection. So this is where you use a back pressure pump or a rig pump diverter. So it needs to have flow through it in order to adjust the back pressure. This is a how do you determine the system surface back pressure loss? You do it during your fingerprinting. So what is fingerprinting is something that we'll discuss in procedures, but give you a brief idea. When you are in casing, as you run to bottom and before you start drilling out the section, you usually circulate through your system at different flow rate to establish various parameters, to check your downhole tools if they're functioning, to check your surface equipment if they're functioning, but you also model your system surface back pressure. So you calculate at, for example, 400 GPM, how much is your back pressure. Now, bottomhole pressure in general is established or is basically in MPD a function of these three parameters as we have been discussing. One is your hydrostatic pressure, your annular friction pressure, and surface back pressure. When you do modeling of bottomhole pressure, that is when you do your designing, you need to take into account multiple scenarios. But these are the most common scenarios that you definitely need to take into account. One is that your bottomhole pressure is static and you are not applying any surface back pressure and there is no circulation in the well. Your bottomhole pressure, what is the bottomhole pressure then? Then you take into account another scenario where your bottomhole pressure is static, that is there is no circulation and you are applying some surface back pressure. What would be in that case your bottomhole pressure? Then there is a dynamic bottomhole pressure where you are circulating and there is no surface back pressure, but you have system surface back pressure. And what would be your with your chokes open? What would be the bottomhole pressure? And then you have your dynamic bottomhole pressure with all the variables like you are applying surface back pressure, you are circulating, and your friction pressure loss, your surface back pressure, and all of this. So these are the multiple scenarios that you need to take into account to see what would be your bottomhole pressure at a particular depth for these different conditions, and is your bottomhole pressure going to be above your formation pressure. So when you calculate your bottomhole pressure without surface drilling, that is circulating, this would be the equation that you would use. When you are doing MPD connections, then you are not circulating. So you only have hydrostatic pressure, but you have surface back pressure. And this is the equation for that. Again, when you are drilling on bottom, but you are using surface back pressure, then you have more components to it. And this is the equation for that. And let's talk about equivalent circulating density. That is a commonly used term in the drilling operation. And basically the equation changes for equivalent circulating density and ESD. So there are two terms. One is in static conditions, you convert the pressure into a static density, that is equivalent density, which is usually measured in pounds per gallon. And in dynamic conditions, you usually convert your pressures into equivalent circulating density. That is when you're circulating. So equivalent static density, ESD, there are no friction pressure pumps are off. But in the annulus could be higher. Contrary due to a gas influx, the average mud weight could be reduced. So this is what it is. You may have cuttings in the well, you may not be circulating, but the equivalent density of your fluid in the annulus would be higher because of these two reasons, or lower. If you are circulating, then your equivalent, basically, the equation here gives you how you calculate your equivalent static density when you are applying surface back pressure. And this plot shows you how your equivalent static density varies with surface back pressure. As you notice, your density becomes higher as you go at shallower depths. So this is something that you need to be aware about, that the pink line over here on the right side shows that your density is higher at shallower depths, and you may need to consider the value of your casing shoe when you're designing this part, as it should not exceed the pressure at the casing shoe and induce losses. So ECD is nothing but when you are circulating, you get additional pressure in the well, and this pressure drop in the annulus plus the hydrostatic pressure applied to the wellbore plus the surface back pressure applied to the wellbore is a combination of the factors that determines ECD. ECD equation is, this is the equation for ECD when you in the context of MPD, and if you can see here, it's mud weight plus your annular friction pressure loss plus the surface back pressure plus divided by the constant and true vertical depth. It is similar to static density, but in which case the annular friction pressure loss is missing. Now here you see, as I was discussing before, calculation, you would notice that you have two values here. One is ECD at bottom and ECD at shoe. Now the casing shoe, the bottom of the well is 12,000 feet and the previous casing shoe is 4,000 feet. Annual friction pressure above the shoe is 140 psi. Annual friction pressure total is 360 psi. So at the bottom, the total annual friction pressure loss will be applicable. And if you see the ECD at bottom is 15.9 ppg, but ECD at shoe is 16.3 ppg. So the value of ECD at casing shoe is much higher than that of bottom, and one should be aware about it, and this needs to be determined. Usually the hydraulic modeling software will provide you a chance, an opportunity to calculate all these things, but one should be aware about the fact that your ECDs may be higher at the casing shoe, and they should be compared to bottom of the well. So these are my additional calculations which we won't be going through in details, but in our future course I will certainly do a lot of exercises associated with this. I will just quickly skim through them and move to the next part of the presentation. As you can see here, basically it is demonstrating that your ECDs are different in different sections of the well, and we should model it thoroughly and ensure that we do not exceed any of the weak formations, pressure at the weak formation anywhere in the wellbore while you're planning your MPD. And typically when you do hydraulic analysis of a particular section, this table will provide you a summary of how you do a hydraulic analysis. Essentially, you need to see, you consider 12.5 ppg mud weight, but the target mud weight is 13.5 ppg. So you consider various parameters at different flow rates, different pressures at shoe, different surface back pressures, different annular friction pressures, and total system pressure. So you do this analysis to find out what is the best suited option for you in a way that your parameters are optimum, you're not exceeding any of the pressures, and you are utilizing an MPD system to control. And you have sufficient margin available with you. Most importantly, that should something go wrong, you should be able to adjust it. So you see the last column is very important here. It says available surface pressure before 14.2 ppg. So how much pressure you can apply more in this whole section is what is important. So this is how it works, and this is how it the planning process is done. So I think we've completed this slide deck, but I have one more slide deck to share.